Right, we are solving Friedmann's equation for dust with a cosmological constant. And I think I will finish this chapter today in 30 minutes or so. And then we will talk about fluid solutions with a pressure. So the equation we have to deal with was K times A is A of t over c squared prime of t squared minus lambda over 3 A of t cubed is a constant. Yeah? So we derived the conservation law for the total mass for the dust, and this gave us this constant with a dimension of a length. So the idea is to solve this differential equation for A, and if we have done this, then we can determine the mass density. What was the factor? 3 A naught divided by kappa squared c squared. This is just a constant prefactor, and the interesting part is this here. Yeah, so if we have found a solution A of t, we plug it into the right-hand side, we get the mass density. Okay, and I have done this. So we have done this already for lambda equals 0. So this was, I think that's how I denoted it, lambda equals 0. And you remember the solutions were these famous three cases. Yeah, that's the scale factor A over t. So that's for k equal plus 1, k equal 0, k equal minus 1. So we could solve this explicitly. Yeah? We introduced conformal time, and then we could integrate this differential equation. Became an elementary integral with a square, with a quadratic function under the square root, and we could solve this in terms of the conformal time. Now I will do lambda different from 0. Oops. In this case, the differential equation can also be solved explicitly, but it gives an elliptic integral. Well, elliptic integrals are not too bad, actually. One can handle them quite easily. Here's one expert in the room who is now doing a lot with elliptic integrals. But actually, I think it's not really instructive doing this here on the board. And for this reason, I will study these solutions only qualitatively. So I will not work out the solutions explicitly, although it could be done. And what's the idea to discuss this qualitatively? Well, that's what we have done already, what I briefly mentioned for the case lambda equals 0, that we view this as an energy conservation law in analogy to classical mechanics, read off the potential, and compare with the motion of a particle in the corresponding potential. And the same thing can be done with a lambda. So let me write this in the form, this differential equation in the form where I have this term isolated. So then I have to multiply everything with c squared over a. So let's see. So let me begin with this term. So this here, a naught c squared over e. Then this term multiplied with c squared over e. So then I have only an a t squared because I divided by a. And I take this to the other side with a minus sign, and I have minus k c squared, and the k is gone, as the a is gone, right? And now you see we have again this form which looks very similar to. Let me write in the mechanical analogy. One would write this as dx by dt squared plus v of x is an energy. Yeah. The x corresponds to the a. Yeah, so what is for the particle? What for the particle is a position along a one-dimensional axis is now the scale factor. The time is a time, and this is a potential here with a minus sign, and the energy is given by k. That's the important thing. The sign of the energy is determined by k. Yeah, that's the important observation. And now let's plot this potential. So if I plot this potential. So let's call this here, so this would be here, I've written x, maybe allow me just to write an a here, then I can just identify this expression here with the potential, yeah? So then this is v of a, and let me plot v of a. Also in classical mechanics, you could call it A instead of X. It would be exactly the same thing. Yes. And what is it? Well, if we don't have the lambda term, we talked about this already, then it's a 1 over A potential with a minus sign. So for lambda equals 0, that's the case we have already discussed, it would be this here. Yeah, this would be lambda equals 0. And then we have, well, the possible values for the energy are minus c squared, 0, or plus c squared. Yeah? This is for k equal plus 1, k equals 0, k equal minus 1. And you see, we have discussed this, and we have even worked out the solution explicitly. If, in this case, well, if I have this end, what does this law tell me? It tells me that this A must always be bigger than the V, because this is a square of a real quantity. So the allowed region in this diagram is a region above the potential, above the graph. Yeah? The particle can move in this region, but this region is forbidden. I would need a negative kinetic energy, which is impossible. So here my particle can move from A equals 0 up to A equals infinity. So it's an ever-expanding universe. Here, the particle, or the scale factor, can move only up to here. Here the kinetic energy must be 0, which means that the velocity, dA by dx by dt must be 0, and then it will turn back. So that's a recollapsing universe. And here, the case k equals 0 is a case where the universe just escapes to infinity in correspondence to this picture. Here I have the maximal point. Here this point corresponds to this point. And then it recollapses. K equals 0 is the case that it stays on the axis, moves on to infinity, and arrives there with a velocity equal to 0. And this is a case that it safely escapes to infinity. And now we have the lambda. What is the lambda term doing? Well, of course, it depends on the sign of lambda. Let's say let's consider the case that lambda is positive first. So then something is subtracted from my original potential. Yeah, because this is a square, something is subtracted. And what is subtracted becomes very big if A becomes big. Yeah, so for big A, this term dominates. For small a, this term dominates. So it starts very similar to what we had. But then this term takes over. And it pushes, because of this minus sign, everything back to minus infinity. So it is doing something like that. Yeah? That's the case lambda bigger than 0. And if lambda is smaller than 0, then again, it begins very similar to the case lambda equals 0. Then the lambda term takes over, but now, because if lambda is negative, I have a positive sign here. Now it goes up to plus infinity. So the curve goes up to plus infinity. So that would be lambda smaller than 0. And well, from these pictures we can read very nicely again the fact that a positive cosmological constant has a repellent effect and a negative cosmological constant has a contracting effect. So it wants to support gravity. So you see, if in the case lambda equals 0, here the scale factor escaped to infinity. If the lambda is bigger than 0, then it will escape all the more, because the lambda, positive lambda, pushes it apart in addition. Yeah? But a negative lambda will actually tends to stop the expansion. And because this term takes over for big values of A. Yeah? So if the universe has expanded because of the initial condition up to a big radius, then at some point the negative lambda will take over and it will push it back. Yeah, so whatever the value of lambda is, it may be as small as you like. As long as it is negative, it will always push back the universe and make it recollapse. And well, so I think these pictures are very, very instructive, and it's easy to see what happens. So we have, in the case lambda smaller than 0, universe is always recollapsing. Always means for all three cases of k, -1, 0, okay, equal +1. Actually, we can calculate, if you are interested, we can calculate the maximal radius which is reached. Should we do this? Let me see. So the maximal I shouldn't say radius, scale factor. Yeah? So in the case k equal 1, it is allowed to call it the radius because it really is the radius of the sphere. But in the other two cases, it is not the radius of anything. It is just the factor with which I have to multiply every distance of co-moving observers. Yeah? Okay, so what's the maximal scale factor? So it's given by the fact that V at the, let's call this A max, that this must be 0, right? This gives, no, what am I doing? No, sorry, nonsense. This must be 0. This must be 0. dA by dt must be 0. dA by dt must be 0. So then we have V of A max is what? It is E, which is minus kc squared. And what was the potential? The potential was this here. So we have minus c squared A naught over A max minus lambda over 3 squared. A max squared is minus k c squared. And, well, we can make plus signs out of everything. And, well, that's the cubic equation, right? So I have lambda 3 squared A max cubed, and this term minus k c squared A max plus c squared A naught is 0, and lambda is negative. Lambda is negative. So if I plot this, so I see at if this variable is 0, I have c squared A naught, which is positive. And lambda is negative, so it's a cubic equation, so it must go to minus infinity. Sorry, it's a negative. Where is it? It goes here down and here up, right? That's it. And you see there must be a 0. There must be a 0 somewhere. There must be a 0. So there is a solution. Yeah, so it's a cubic equation. It's not sure that a cubic equation has a positive real solution, but this cubic equation does. And that's the way in which you can determine the A max. So it's a unique positive real solution of this cubic equation. This is the A max. And you see it depends on the relation of lambda and A naught, how big this maximal radius is, right? So if lambda is 0, then it doesn't work, right? Wait a minute, let me see. It works. No, it only works for negative k, right? No. Oops, what have I done? So if I'm in the case lambda equals 0, this is this case, then I have this is positive k. This is positive k. For positive k, I have a turning point. Did I make a sign mistake? So with lambda equals 0, I must find a solution. A max, this is this here. Yeah, this is this here in this case. For positive k, yeah, that's right. For positive k, this has a solution, a real solution, right? And for negative, it does not. But with a negative lambda, it always has a solution. Okay, so that was the case. Lambda smaller than 0. Quite easy to discuss this. The case lambda bigger than 0 is a little bit more complicated. There we have to distinguish several cases. So if lambda is bigger than 0, so what do we have then? Yeah, then let's look at the picture. Then it depends on where this maximum is. Right? Here is our energy level. And the question is, does it hit the increasing branch of the function, or is the maximum so low that it goes over the maximum? So we have to determine the maximum, and then we have to distinguish 3 cases. That this is bigger than this this maximum value, that is smaller or that it is equal to it. Okay, so let's do this. Maybe I do another picture because I want to, for this case. So for this case, this is the case lambda bigger than 0. Here I have something, so this is A, VA. How should I call this? Should I call this? No, I shouldn't call it again A max, it would be confusing. And A naught is also already used. How should I call this? Say A capital M, yeah? Like maximum of the potential. And here I have V of A of capital M. And now the question is minus C square, is it bigger than V of AM or is it smaller than V of AM? That's the question we have to discuss. Oops. So what is, now this is determined by the derivative. Yeah, I was jumping ahead when I discussed the other case. Now I have to calculate the derivative of the potential. So V of A was what? Let me write it again. It was minus C squared over A naught minus lambda over 3 C squared A squared. This means the derivative of the potential is minus times minus is plus C squared over A squared A naught, and this gives minus 2/3 lambda C squared A. And this is supposed to be 0. 0 for A is A max, A capital M. So this is, well, it's the same cubic expression which we had there. So let me take this to the other side. Then I have 2/3 lambda C squared A cubed. I multiply with A squared. And on the other side, C squared A naught, where A is now this AM. And so I see AM is the third root out of this expression. I have a 2 here, a 3 here, lambda C squared to the 1/3. Okay, that's it. So this is this AM here. And now I have to see what's the value of the potential V at this point. And I have to compare it with minus C squared. So V of AM is what? So if I insert AM for A in this expression, I get minus C squared A naught AM minus lambda over 3 C squared AM squared. And I have to see if this is bigger or smaller than minus C squared. So if I insert the AM, maybe it's a good idea to write this factor in front of the bracket, minus C squared A naught over AM. Then I have a 1 here, and I have a plus here. The C squared is outside, but I don't have an A naught. 1 AM is outside, so I have lambda over 3 C squared AM cubed. Okay? And for AM, I can now insert this expression. So this is minus C squared A naught. What was AM? AM was this here. So let me write it with let me write the inverse to the power 1/3 T 2 lambda C squared over. Here's the C squared cancel, right? Don't have to write it. 2 lambda over. I've taken this out of the bracket, thank you. Yes, there's no C squared. Okay, so this comes with an exponent 1/3. And then this is 1 plus lambda over 3 A naught, and now AM cubed. So this goes away then, and I have 3 A naught divided by 2 lambda. This goes away, and this goes away. So it's just 1 plus 1/2, that's 3/2, right? Minus C squared A naught, this gives us 3/2. And then I have this expression. And I have to ask, is this, I have to compare this with minus c squared, right? So if this inequality is true, if this is actually bigger than minus c squared, then I have a recollapsing universe, right? But if the other inequality holds, then also this, as a case k equal plus 1 gives an ever-expanding universe. So let's see, what does this mean for lambda? So if I cube an equation, then the minus sign stays a minus sign, right? So, I have minus signs on both sides. So let me multiply with minus 1, then I get plus signs, right? So I get 3/2, 2 lambda, 3a naught. And now this is the other order, right? C squared. I multiplied with minus 1. This means the inequality sign is inverted. So this gives 2/3 lambda over I naught must be smaller than, and the c squared can be cancelled, right? And here I have 2 over 3 a naught cubed. So I must have lambda smaller than 2 to the power 3, I think is 8. I have another 2 here, so I have only a 4. Then this is 3 times 3 is 9, right? And here I have an a naught squared and another one here, so an a naught cubed and another one here, so I am left with this squared. So this is let's call this lambda critical. That's a critical value of lambda. We are talking about the case that lambda is positive, so this is really a value which is allowed for lambda. Yeah? This is a critical value which decides if the universe with k equal plus 1 escapes or if it does not escape. So we can say, we can now summarize the results. So for k is equal to minus 1, then we are here. And we are here, and this expands forever. Forever, so universe expands forever. And it goes to infinity. Yeah? So the scale factor becomes infinite in the limit. For k equals 0, the same is true. And it arrives, if we have a positive cosmological constant, it arrives at infinity with a finite velocity. And now comes a case where we have to distinguish several cases. So here we have 3 cases to distinguish, namely lambda smaller, bigger, or equal than. So we have, if lambda is, let's begin with a case that lambda is, say, smaller than. Then, if lambda is small, then I have this inequality. So the maximum of the potential is bigger than minus c squared. That's the situation I've drawn here. And then the universe is recollapsing. So if lambda is equal to lambda critical, this means I'm just approaching this maximum. So if I arrive here at this point, I have I arrive there with velocity 0, but then the particle can return. Here I approach this asymptotically, and I arrive here asymptotically with a velocity 0. So the particle can, or the scale factor can actually never return. Yeah, it moves on and on and on and on and approaches this asymptotically, but it never arrives here. So it asymptotically tends towards a finite value of AM. It's different from the case k equals 0 without a cosmological constant, where it asymptotically went out to infinity. Now it went asymptotically to a finite radius. So universe expands forever, but it only goes towards a finite value AM. Yeah? So we have k equal plus 1, so this is a sphere. The natural topology is that of a sphere. It blows up, becomes bigger, 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 and asymptotically approaches a finite value. So this is this boundary case where lambda is just the critical value. And where the last case is clear, if lambda is bigger than lambda critical, yeah, then the repellent effect of the cosmological constant takes over, and we have universe expands forever to infinity. Yeah, so then we are above the maximum, so then it goes out to infinity. So we have another critical behavior here, as we had in the case lambda equals 0. In the case lambda equals 0, the critical behavior was just characterized by the case k equals 0. Yeah? So for k bigger than 0, we had a recollapsing universe. For k smaller than 0, we had an expanding universe. That's different here. Here's a critical behavior. There's a question of whether or not the universe is recollapsing is not related to the value of k. So it's not, does not distinguish different values of k. It only occurs for k equal plus 1. And then it is determined by this inequality. Yeah? So the two cases which coincidentally coincide here do not coincide here. So here the critical behavior means spatially negatively curved or positively curved, and forever expanding or recollapsing. Yeah, the borderline case for these two situations is the same. Here it is different. So we have discussed the behavior, the critical behavior as far as recollapsing property is concerned. We do not have discussed yet the critical behavior as far as the sign of k is. And that's what one calls the critical density. Yeah? One could use the word critical density in two different ways, but if one does it in this way, then it would depend on the lambda. So if one would call as a density, A naught gives the density, right? A naught determines the density. So if one would call this a critical density, then it would be critical in the sense that it distinguishes between forever expanding and recollapsing. But that's not what one means when one speaks of a critical density. What one means is a case that the borderline case between positively curved and negatively curved. Yeah, and that's what we want to discuss now. So the critical density. And this can be done in principle for both cases of lambda. The physically relevant case for which it is usually done is a case lambda bigger than 0. But the equations which I'm writing down now hold for all values of lambda. So what was the idea? The idea was when we introduced the critical density for a dust, you remember, yeah, and this gives then rise to this parameter which one usually calls omega m. Yeah, omega m is a real density divided by the critical density. We want to do something similar now with a cosmological constant, so we have to bring the density into the game. So I have to write the differential equation again, but now in a way that the mu occurs explicitly. So I have the equation k, a, should I write the arguments? Okay, let me write it. Plus a of t over c squared, a prime of t squared minus lambda over 3 a of t cubed. And on the right-hand side, I have the a naught. And now I re-express a naught in terms of the density and the scale factor. So I have, what is a naught? A naught is kappa over 3 c squared mu of t a of t cubed. Okay? I want to write this as an equation of densities. So I divide by everything which comes with the density here. So I divide by this prefactor, 3 divided by k c squared, and then I have an a cubed. So this gives k divided by a squared plus a prime of t squared over a squared, c squared, minus lambda over 3. This is mu. This is the density. Okay? And, well, I multiply this out, and I want to have the term with a k on one side. So let me write it this way. Let me multiply this out. And let's take everything else to the other side. On the other side, I have the mu. And then these two terms with the other sign. So I get minus 3 over kappa c to the 4 now. A prime of t squared divided by a of t squared. And the factors of 3 cancel, so I have minus lambda. No, I took it to the other side, right? So it's plus lambda divided by kappa c squared. So because this is a density, a mass density as far as the dimension is concerned, these quantities must also have this dimension. So I have an equation between densities. And you see, these two densities together here, they decide whether... would you allow me to interchange this? Because I want to underbrace it. It's easier to let me write this in the other order, the same expression. Let me begin with the lambda. This had a plus, right? Lambda over kappa c squared minus 3 a prime of t squared kappa c to the 4 a of t squared. Yes, that's it. So, so these are densities. That's what I was saying. And the combination of these three densities, that's a true density. That's a density which is made out of the cosmological constant. And that's something, yeah, which involves the Hubble constant, which I evaluated and at the time TO, right? So, and this combination on the right-hand side decides whether this here is positive or negative. And the sign of the left-hand side is completely determined by k. So if we want to distinguish the three cases, k positive, k negative, k zero, we have to check whether or not this here is positive or negative. And the usual way, what one does is one calls this mu of c. Or let me write it in a slightly different way. Oops. I want to read this. How should I do this? Now it becomes difficult. Let me see. I get this up. Yeah, I think this works. So this equation, let me write it again. But let me evaluate it at a point TO, which we interpret as our observation time. Kappa c squared a of TO squared is what? So it's mu of TO, the density now. The density now, plus this is a constant, has nothing to do with at which time I evaluate it, lambda over kappa c squared. And then I have this expression which involves a Hubble constant, right? So this is 3h of TO squared divided by kappa c to the 4. And this here is what one calls the critical density at time TO. So the critical density depends on time. Yeah? All our parameters depend on time. The Hubble constant depends on time. The acceleration, the deceleration parameter depends on time. And also the critical density and thereupon the density parameters depend on time. One usually evaluates this at a time which is interpreted as now. And then for the astronomers, they are constants, yeah? Because TO has a particular value. So if you look in a cosmology book written by an observational cosmologist, then all these things are treated as constants. Yeah? But of course, they depend on the time when the observation is made if you evaluate a theoretical model. Okay, and now we can decide that we read that k is bigger than 0 if and only if mu of TO plus 1, or lambda, it's not a 1, it's a lambda, the cosmological constant, is bigger than the critical density. Now we can shift this. Oops. Okay, k equals 0 if the equality is true, and k is smaller than 0 if it's the other way around. And as before, it's now common to introduce these density parameters. Now we have two. For the dust alone, without the cosmological constant, we had only one. So what one does is one divides this expression by the critical density. So we have 3k kappa c squared A of TO squared divided by mu c of TO. Then I have here the true density as it is now divided by the critical density plus the cosmological constant divided by the critical density and these other constant coefficients. And you see that, well, that is what one calls, we had this already. This is what one calls the omega matter. Yeah? Matter is what is described by a dust. It's the ordinary matter. And it also includes dark matter. I will talk about dark matter next week in detail. It also includes dark matter as long as the pressure of the dark matter can be neglected. And that's what one calls cold dark matter. Yeah? Cold matter means matter where the pressure is neglected. So you could read this as the density parameter for ordinary matter, ordinary baryonic matter, and cold dark matter. But I'm jumping ahead when it comes to this. And this is something, yeah, which is also a dimensionless parameter. I have divided two densities, one by the other, so it's dimensionless. And it's constructed in the same way as this expression for matter, but now for the lambda, and that's what one calls omega lambda. Yeah, the omega parameter for lambda. It depends on TO. Yeah? Although this expression, the density which is associated with lambda is constant. Yeah? But because I divide by the critical density, the whole thing becomes a function of TO. So also this thing is not a constant. And now we can say for k equals 0, the k equals 0 case, we have omega m plus omega lambda is 0. It's 1, sorry, it's 1. It's 1. No, what? What did I do? I forgot the term. I forgot the term, sorry. This would be complete nonsense. Here, look, I forgot this term, and this becomes now 1, yeah? Mu critical divided by mu critical. And of course, then it becomes 1. So the two omegas must add up to 1 if I have k equals 0. Yeah? And as we will discuss in detail, there's fairly good evidence that we are in the universe with k equals 0. We cannot be absolutely sure. I'm not saying that all the other models are completely out of the discussion, but k equals 0 is a favorite model at the moment. And then if we have a dust and a cosmological constant, then the two density parameters should add up to 1. So only one is an independent quantity. The other is undetermined, right? And a little bit later, we will introduce radiation. Then we will have a third omega. And then we can determine 1 from the other two if we assume k equals 0. So that's what usually done in cosmology, in model building. Okay, so we have now the omega m and the omega lambda, and they're important quantities which you should know how they come about. As I said, this works mathematically for positive and negative lambda. The somewhat strange thing is that the density which you associate with a negative lambda would be negative, yeah? And also the omega lambda would then be negative. So, but mathematically it works. There's a question?
Yes, what would happen if we make also lambda time dependent?
Then it would. The question was what would happen if I make the lambda time dependent? If I make the lambda time dependent, this is no longer a cosmological constant. Yeah? Yeah. So the left-hand side of Einstein's field equation is fairly good motivated. Yeah. There's this famous Lovelock theorem, which says if you want to have it on the left-hand side of the field equation, on the right-hand side there's the energy momentum tensor. If you want to have on the left-hand side something which is made out of second derivatives of the metric, no higher than second derivatives of the metric, and which satisfies the conservation law, then it is fixed already. Yeah? You do not have to require symmetry. Yeah? Lovelock actually wrote 2 papers. In the first paper, he assumed symmetry. Then the proof was fairly simple. And in the second paper, he showed that actually symmetry comes out automatically. And then the proof becomes much, much more difficult. Yeah? But you don't need this assumption that the thing is symmetric. It comes out automatically.
So basically, we have to change the physics behind it to make the lambda time dependent so that there's matter creation more.
Yes, what you can do, of course, is you can write the term which contains a lambda on the right-hand side and say this is a kind of matter. Yeah? This you can always do. But if you want to have it on the left-hand side, if you want to have everything on the right-hand side interpreted as the energy momentum tensor, which should satisfy the conservation law, then you cannot make the lambda dependent on any parameter. Or you would give up the conservation law. Yeah? You would say energy is no longer conserved. Yeah? But this is a big step, and I would really shy away from this as long as there are really compelling reasons for doing this. Actually, the conservation laws, the basic conservation laws, are, I would say, the most solid fundamentals of physics which we have. I wouldn't give up any of them without very, very good reason. Okay, so much for the... Yeah?
So can K change in time? For example, if we now observe that it is 0, can it be...
Yeah. Okay, the question was whether K can change in time. Well, in the mathematical formalism, as we set it up here, it cannot. Yeah? Because we define the Robertson-Walker universe in a way that it cannot change. But yeah, you can. What can we do? Is this topologically possible? To construct a universe which looks like our Robertson-Walker universes, but then we should work with a capital K, remember? We introduced a little k as a normalized capital K. The capital K could take on every real values. So could I work with a capital K which goes through the value of 0? Is this topologically possible? Yeah? So I said the natural topology for k equal plus 1 is a sphere. Of course, you can consider what is it called? The covering spaces. Now I have the word. Topological covering spaces, which are no longer compact. Yeah, and can this have the topology which I need for a universe with k equal 1 or k equal 0? Actually, I would think it does not work. Yeah. And the other way around, I'm sure the other way around it does not work, because if I want to have, I can compactify a universe with k equal -1, but I'm fairly sure I cannot compactify it to a sphere. I can compactify it to tori and things like that, and other topological things, but I think I cannot compactify it to a sphere. So I think it's topologically not possible to do this. And yeah. I'm not sure what the physical meaning of this would be. So the way in which we set up everything simply doesn't allow this. Yeah, but
for example, this means that if we now measure k and it is 0, then it remains 0 forever.
Yes. So in this setting in which we wait a minute. Yes. In which we work with the equation. But actually we have derived this differential equation from the field equation under the assumption that k is constant. Yeah? So we didn't have a capital K which could be differentiated, yeah? which had a derivative different from 0. So the equations wouldn't be valid. If I just leaving open the question whether or not it is possible topologically, but in any case it would be described by a different equation. Yeah? So here the little k only takes these three values. We don't discuss anything else. Okay, did I want to say anything more about the case with lambda? Or I think this was it. Yes. And now we do other perfect fluid solutions. So we had the vacuum solutions. We discussed them fully. We had the dust solutions, which I discussed fully without cosmological constant and at least qualitatively with cosmological constant. And now we have, should be C, perfect fluid solutions with pressure. Okay, so let me write down the equations. So now it's the first time that I use the full Friedmann equations in their full generality. These were the equations which I called F1 and F prime, F1 and F2. Up to now I had always something like an F1 prime or an F1 double prime where I had a 0 or a constant on the right hand side. So now I have the general equation. So this was write it in this way as we derived it from the field equation squared. A of t squared minus lambda c squared was kappa mu of tc squared. This was the equation F1. And the second equation, which we actually haven't used, where we have shown that it's not necessary to use it, yeah, because it was always already implied by the other equation, which we are working with, which we have been working with. But of course it is there. So this is kappa pressure of T, A of T squared. Okay, so these are the two equations. This was F2. Well, and now the first thing we have to discuss is what we actually want to solve. Yeah? If I allow for, if I consider these two equations, and I allow the mu and the p to be anything, if I don't say anything about mu and p, then the equations are always identically satisfied, and I don't have to solve anything. Yeah? You give me your favorite Robertson-Walker universe. This means you give me the scale factor and the little k. They fix the geometry. Yeah, the scale factor and the k fix the geometry. They give the metric. Then I may choose any lambda I like, and I define the mu and the p by this equation. And they are satisfied. I don't have anything to solve. Yeah? So they are identically satisfied if I don't make any assumptions about mu and t. What that means by solving this equation means make an assumption about mu and p, and then look at it as a differential equation for A. And we have done this for the case first that both are 0, and for the case that this is 0 and this is positive. And if we don't make any assumption, we don't have to solve anything. So we need to make some assumptions in order to have a problem to solve. And what I want to do is I want to discuss the solutions not fully, but for some special cases where these two things are related by an equation of state. Yeah? So if they are allowed to be completely independent of each other, then we don't have anything to solve. But before I do this, let me say a few words about the static solution. Oh, no, there's another thing that I should do first. I said you can give me the A and the K, and then I still have the freedom to choose the lambda as I like. And then the mu and the p are determined. So there's an ambiguity as to the choice of the lambda. So you can say, if I have chosen the lambda, you say, I don't like your lambda, I want to have another lambda. So you replace lambda by lambda, say, plus lambda 0. Yeah? Then the solutions are still satisfied, but with a different mu and with a different p. So how do I have to, these are constants. Yeah? Lambda is a constant, and also the new lambda must be a constant. So mu transformed into mu, so I add something to lambda, so I have a minus sign here. So I need minus lambda naught. Is this true? Is it c squared in both places? No, this is a 4 here. This is a 4. So I have to add by c squared, divide by 4. Let me see. This is divided by c squared, right? Divided by c squared and multiplied by kappa. Is that true? I think so. Yeah, that's the transformation. If I make this transformation, then the first equation remains as it was. And the p here have the other sign. That's an important thing to note. Here I get a plus. I get a plus lambda naught over times kappa, and there is no c. Yeah? P has the same dimension as mu times c squared. Yeah? Mu times c squared is an energy density. Mu is, as far as the dimension is concerned, the mass density. And the dimension of mu and p differ by a factor of c squared.
Shouldn't it be mu case divided by kappa, because when it passes kappa divided by kappa and have the kappa in front and the divided by kappa?
Right? You're right. Thank you. Thank you. It is this, right? It is this. Yes. The c squared is correct, right? I think it's that. Yes. Thank you. Okay, so there's an ambiguity. But you see, you cannot, there might be a special reason why you choose a particular lambda. Namely, at least the mass density or the energy density we want to have positive. Yeah? We don't want to have a negative mu. And you can achieve this by shifting the lambda appropriately. What you might get is that you spoil the sign of the p. If you want to make this bigger, then you need a negative lambda. But this makes the p smaller. Yeah? So it might push the lambda into the negative regime. So if you want to make one as big as you like, then you usually make the other one smaller and the other way around. Okay, but apart from this, you can shift the lambda to the other side. Actually, we have done already on one of the worksheets a little problem with this, where this was employed, this observation. Namely, we looked at the zeta universe with a flat slicing with k equals 0. So this is, as we know, a solution to the field equation with a cosmological constant, but no mass density and no pressure. Yeah? So mu and p are 0. But you can reinterpret it by, so the original mu was 0. We can say our original cosmological constant now becomes a mass density, or energy density, I should say. And our original lambda becomes this pressure. Yeah? And you see, only one of them can be positive. So if we have, the signs are, I'm funny. Wait a minute, for the zeta universe has a positive cosmological constant, and for this I should get a negative pressure. So I think there's again a sign mistake. Where's the sign mistake? It should be the other way around. Was this here correct? Let me see, minus. Yes, it's correct.
Yeah, but when you add the term, the lambda naught, you get it with a positive sign on the right-hand side, so the mass density should increase.
Let me see, I write this to the other side, then the sum of them should be invariant. And the sum of this is invariant, so I think it's correct. You remember we did the problem, right? And it came out the way that for the de Sitter universe, where we have lambda positive, and we start with mu and p equals 0, the transform things have a positive mu and a negative p. I'm confused now. Yeah, the signs are as they are, and I think yeah, it's also here, right? Here's a minus, there's a plus. But we did the calculation, it came out correctly as well.
But when you look at the second equation,
yeah.
You insert lambda plus lambda naught.
Yeah.
You shift the lambda naught term to the right hand side, and then you
No, I also transform the p. I transform both. I transform the lambda and the p.
Yep.
And the resulting equation should be the same as it was before. So I add it here and I add it here. And then I get...
But these two, the p of t transforms into some... I mean, this is not the same p of t then. And what you know is this...
This is the old one, and this is the new one.
Right, so the new one is smaller.
So if I transform this into this, and this into this. The two terms with lambda naught cancel, right? No, here's a factor missing, of course, over kappa. So if the equation holds with the new ones, then they also hold with the old ones, and vice versa. Oh, I think it's correct this way. Or should I say, wait a minute, these are the old ones, but it cannot depend on this, right? Wait a minute, this is the right way of looking at it. I want to have this equation. I want to have this equation. And I write it by adding these two terms here. And let me see. And this means that the original, no, that is then the original lambda. That the original lambda was my new lambda minus lambda naught. And my original p was the new p minus lambda over kappa. The original one was, yes, of course. I want to kill, when I want to reinterpret a cosmological constant by a perfect fluid. Sorry, I think everything is correct. Then I want to have the new ones, the new mu and the new p equal to 0. I want to make a transformation that the new p and the new mu are becoming 0. Then my old one must be minus lambda naught over kappa, and my old mu must be plus lambda naught over c squared over kappa. So this is positive and this is negative. So everything is fine. Yes. Yeah, sorry, this is that's a kind of logic which sometimes can confuse a little bit. Okay, so you see there's this ambiguity, and actually this was a fairly vivid debate at the time when Einstein gave up the cosmological constant. Yeah, he had introduced it in 1917. We have talked about the reasons, and then the expansion of the universe was discovered in the late 20s. It was Lemaitre, Hubble, and so on. And Einstein said, okay, I accept this, the real universe is expanding, forget about the cosmological constant. And some other people said, oh, maybe we should keep it, and maybe it is relevant, and there was a debate going on. And one viewpoint, it was voiced in particularly by the British cosmologist William McRae, was this is a completely irrelevant debate. Yeah, there's no substance to this debate whatsoever. If you want to write the equations with a cosmological constant, do it. If someone else wants to do it without a cosmological constant, he can easily do it. He just shifts the lambda term to the right-hand side and says it's a kind of matter. It's the same equations which we are discussing. If you have a cosmological constant or not is completely irrelevant from this mathematical viewpoint. This is mathematically correct. But of course, for the physical interpretation, it does make a difference. Yeah? For the physical interpretation, it does make a difference. So for instance, if you discuss if there's an equation of state between mu and p, or if we discuss what we just talked about, what are the signs of mu and p, then of course it does matter. Excuse me. And of course, it does make a difference. So we will keep the lambda. We'll keep the lambda on the left-hand side. But we'll have in mind that we always have the freedom of reinterpreting it as giving rise to a perfect fluid with a certain mass density and pressure. Okay, this was the first remark which I wanted to make before we start solving this for particular equations of state. The second remark is on the static solutions. If we did the dust with a cosmological constant, and we wanted to do it with a positive density mu, we have seen that it works only for k equal plus 1. Yeah, this gave Einstein's static universe. So static solutions for a dust with a cosmological constant with a positive density are possible only for k equal plus 1. K equal 0 would be vacuum, and k equal minus 1 would require a dust with a negative density, which we don't want to have. Let's see how this changes if we allow for a pressure. So where are the time derivative terms here? So I set them equal to 0. Then I get this divided by a. This is now a constant. I don't know, should I write it a naught, or let me just, this is gone because the derivative is 0. Minus lambda c squared is kappa mu must also be a constant, c to the 4, and minus k minus 2ac squared. Oh, this is 0. This is plus lambda a squared is kappa p a squared. And let's see, can we do it with a negative k, and maybe also with, in a non-trivial way, with k equals 0? Well, let me see. How do we get the k? Let's get rid of the lambda. So let's multiply this with c squared over a squared, and then add the two things together. So I get 3 minus 1 is 2. 2c squared k a squared. These two terms cancel. And here I have kappa c squared mu times c squared plus p. Okay? And now you see, if you want to do it with a negative k, you must have either mu or p negative. So it doesn't work with both positive. So if p bigger than 0 or maybe equal and mu, then we have necessarily, or let's say this is strictly bigger than 0, then I only have the case with k equal plus 1. And k equal plus 1, and the constant scale factor is Einstein's static universe. Yeah? But if you allow for, at least for a negative pressure, yeah, if the pressure is big enough so that it dominates this term here, then you can form a static universe with a negative k. So this means a static hyperbolic universe. It is possible with a negative pressure. So we have 3 cases now. All 3 cases are possible if you allow for a negative pressure. So we have k equals 0. This is, of course, with a constant scale factor, this is Minkowski space, right? So in this case, it works with everything 0. Lambda equals 0, mu equals 0, p equals 0. Yeah? You can choose another combination. Here you always have the freedom to make transformations of this kind. You can say, no, Minkowski space is a solution with a cosmological constant, but I have a funny kind of matter on the other side. Yeah? You can do this if you like to. Then we had k equals 0. That's what we have already discussed. This is an Einstein static universe. Einstein static universe. Yeah, it's a cylinder world. You have a sphere of constant radius, and it just sits there for all time. Yeah? This is Einstein's static universe. So again, you have several possibilities, but the simplest case is to say it has a positive lambda, a positive mu, and no pressure. Yeah, in this way, we have discussed it already. And now we have a new possibility. We have also the possibility to do it with k equal minus 1. I think this has no name. Yeah? So it's hyperbolic space, it's a negatively curved 3 space, and it sits there for all time. Yeah? So this is, in the literature, I've seen it sometimes called a static hyperbolic universe. Well, that's obvious what it is. Static, and the quantum field theory people occasionally do calculations in this space-time. Static hyperbolic universe. But I think it's not named after anybody. And this, whatever you do, it requires negative pressure, or negative mu, which is even worse. Yeah, so I would choose a negative pressure and a positive mu. Okay, so these are the static solutions. So if you allow for a pressure, and if you allow the pressure to be negative, all 3 cases are possible now. That's the difference in comparison to the dust solutions. And now with the static solutions out of the way, we can do the same thing which we did for the dust solutions. Namely, we can introduce a conservation law. And then, in a sense, this makes the second equation redundant, but only in a sense. So the conservation law for the dust universe, you remember, was just that for dust, you recall, For dust, we had the conservation law. It was still on the board today. That this is constant. Yeah? Would you expect this law also to hold with the pressure? We will check it mathematically. Yeah, the mathematics will tell us whether or not it holds. But before we do the calculation, what do we expect? Do we expect this to hold? Now we have a perfect fluid with the pressure. But if you have a dust, then this is just the rest mass density of the dust particles. This is multiplied, this is a factor by which the volume scales. So mass density times volume gives the total mass in this volume, and this must be constant in co-moving coordinates. But now we have a pressure. What do you expect?
But this is energy conservation, right?
Well, I said for dust, it is just the rest mass density. Now it's no longer just the rest mass of the particles. You're right. Now we have a pressure, so it's the pressure gives a contribution to the rest energy, right? So you say you would not expect this. The pressure is doing something, and actually it is doing something. So does not hold with P different from 0. And well, I think it is obvious if you think of the first law of thermodynamics. First law of thermodynamics. Yeah, we have a gas, and the differential of the energy, du, is minus TdS. Here's a plus, right? Minus PdV. I think that's it. Yeah, if you have a gas, then you may. This is the heat. The one form which describes the heat. Let's assume our gas is thermally isolated. So there's no heat flow. Then the only way in which you can do work is by changing the volume. But changing the volume is precisely what happens in an expanding universe. Yeah, the volume changes, and we have a non-zero pressure. So this term is non-zero. So we don't have conservation of the energy. Yeah. So we have a contribution from the pressure. And actually, Einstein's equation will tell us that this is true. So we will derive it from Einstein's equation. We will derive an equation which is quite analogous to this. So this is the quantity which we had before, and now we have a contribution from the pressure.
But we assume that entropy is 0, right? Not a constant.
I said this is the heat. This is the heat. Yeah. Yeah, so it's, well, in the old-fashioned way, it's usually denoted this way, right? It's not a D of anything. That's why some people make this stroke through the D. So it's a one form which describes the change, the heat going into the volume or out of the volume. Yeah, and if you assume that there's no such heat flow, actually, when we assume a perfect fluid, we don't have mixed terms. OI components of the energy momentum tensor. Here the energy momentum tensor has just the pressure and the energy density in the diagonal. It doesn't have off-diagonal elements. And such a term would correspond to off-diagonal elements in the energy momentum tensor. So that's the reason why we don't have such a heat flow here. And then the only way in which you can do work with your system is by changing the volume. Yeah? And if there is a pressure, and if we are in an expanding universe, then this term is non-zero. Okay, but let's derive the conservation law. So let's not speculate what could come out. Let's just calculate what mathematics tells us. So let's derive the energy balance with pressure. So let's derive it. Of course we need, oh, did I erase equations F1 and F2? No, hopefully not. There they are. So I think I leave it as it is from F1. Or do I multiply it with a cubed? Let me see. Yeah, maybe it's convenient to multiply it with a cubed. So let me write kappa c to the 4 v of t, and I multiply everything with a cubed, and I want to differentiate this with respect to t. So this is the same as d by dt of this equation multiplied with a cubed. So this is 3 squared k, 3 a double. I drop the arguments now, I think. Or anyway. I multiplied with a cubed, so I have one factor of a minus lambda c squared a of t cubed. Maybe I can also divide by 3. And this 3 is gone. This 3 is gone. And here I have a 3. Let's differentiate this. We have done this before, actually. Yeah, so for the dust, this came out as 0. Now it will not come out as 0. But this gives nothing. So then I have, I forgot a factor of a here, right? I multiplied with a cubed, so I get a factor of a here. So I have c squared k a prime of t. And plus, if I differentiate this, I get a prime cubed. And if I differentiate this, I get 2 times a prime, a double prime. And here, the factors of 3 cancel. I get lambda c squared a of t squared a prime of t. And now I can extract the factor of a prime. I have c squared k plus a prime of t squared plus 2a of t a double prime minus lambda c squared a of t squared. And what I have in the curly bracket is, as I very much hope, the left-hand side of F2. Let me see. With c squared multiplied, right? With minus c squared multiplied. Yeah, if I multiplied the equation F2 with minus c squared, I get this, then I get this, then I get this, and I get this. So this here is by F2. It is minus c squared times the right-hand side of F2, and the right-hand side of F2 is, kappa p of t a of t squared. Okay? So if I combine this, I have minus c squared kappa p of t. And here I have the square of a times the derivative. That's the derivative of the third power, right? So this is d by dt of a of t cubed. I don't have a factor of 3, so I think I have to multiply with 1 over 3, right? So if I differentiate this, then I get 3 times a squared, and the factors of 3 cancel, so I get this term here. And from the chain rule, a prime of t, so it's the same thing. And now you see the kappa times what? Kappa times c squared over 3 cancels on both sides. So I can rewrite this as the following: d by dt of c squared mu of t a of t cubed. Yeah, this is the energy density, the rest energy density. That's a scale factor which determines the volume. So this is the energy inside a certain volume, which I consider in co-moving coordinates. And on the right-hand side, I have minus, I divide it by c squared k over 3. So I have just minus p d by dt, the volume factor. See the analogy? Differential of u is minus p times differential of v. Yeah, it's the first law. It's exactly the first law which we get here, which we derived from Einstein's field equation. And so this law has not, I call it the energy balance, yeah, because it has not the form, in general, not the form d by dt of something is 0. And as long as mu and p are completely unrelated, yeah, there is no, you cannot rewrite it in this way. You cannot write it in the form d by dt of something is 0. But if you have an equation of state, then you can write it in this way. And then you have, again, a conserved quantity. Yeah? So if you start out with any Robertson-Walker universe, calculate the right-hand sides mu and p from the left-hand sides, you will end up with this equation, and you won't get any conserved quantity. But now let's assume that we have an equation of state. Well, what's an equation of state? Well, quite generally, an equation of state is something of the form f von t and mu is 0. Yeah? And we call it an equation of state if this function capital F does not depend on the coordinates. Yeah, otherwise it would be something trivial. You could always, if you give me any function on the spacetime p and any function mu on the spacetime, you can, with appropriate factors which depend on the spacetime point, you can always satisfy this equation. Yeah? The crucial thing is that the f does not depend on the coordinates. So in our case, in the Robertson-Walker universe, p is a function of t and mu is a function of t, but there's no other t flying around in this equation. Yeah? The rest does not involve the space-time coordinates. And usually one even requires more, well, not always, but in many cases, one requires that also no other properties of the fluid are involved. So for instance, you could assume that the temperature also occurs. Yeah? So you have a function of pressure, density, and temperature. That's what we would call a baroclinic equation of state. And they are used, for instance, for the atmosphere. They are used. Yeah. But for the simpler case, in simpler cases, we assume that we have no dependence on nothing else. So they are just constants in this function apart from p and mu, and that's what we call a barotropic equation of state. Yeah. So this is barotropic, meaning that the function f involves only constants, yeah, parameters, which characterize the medium. And well, actually, if I will calculate I will do the calculations for a very special barotropic equation of state. In particular, an equation of the form that the pressure is just proportional, which depends on t, that the pressure is just proportional to mu. And for dimensional reasons, I need a factor of c. Now the two sides have the same dimension, so what is in front of it on the right-hand side is just a number. And this is usually called w. And it's a constant. It's really a constant with a constant w. So for this case, we want to evaluate this law and then the differential equation. So you know already one example, namely w equals 0. That's a dust, which we have done already, right? Actually, w equal minus 1 is what we did in the worksheet when we reinterpreted the de Sitter universe. Yeah? So w minus 1 gives dark energy in the simplest way, where we just interpret the term with a cosmological constant as a perfect fluid on the right-hand side. And there's another important case, which I will do in a minute. This is w equal 1/3. This is the radiation. That's a photon gas. Yeah, it's a model for a photon gas. So these will be the three cases which we will consider. But actually, this law, this energy balance law, can be evaluated for any w. And let's see what we get. So then So our energy balance law now says the change of the rest energy, the rest energy density multiplied with a scale factor cubed, minus p. What is minus p? Minus p is minus w c squared mu over t d by dt a of t cubed. And what I want to do is I want to write this under one-time derivative. I want to write it in the way d by dt is d by dt of something is 0. How do we do this? Let me see. Let me check what's the most clever way of doing this. Oops. Did I multiply this out? Yes, I think I multiplied out. Yeah, I multiply this out. First of all, the c squared is spurious. So I have mu prime. Let me write it this way. d mu by dt a cubed plus mu. Then from the derivative I get 3 times a squared dA by dt. And on the left-hand side I get minus w mu 3 times a squared dA by dt. So these two terms can be combined. So I have, what about the sign? Yeah, it's correct, it's correct. So I get minus 3, 1 plus w, right? Yes, that's fine. A squared dA by dt. Well, I can divide both sides by a cubed. And I think I can integrate this. Yeah, I think I can integrate this. So I have, no, what have I done here? Something is wrong. Oops. I need an exponent. Wait a minute. Something must be wrong, yeah. Yeah, mu is, yes, of course, a mu is missing. Where is it? Here, this mu, I just forgot this mu. Is it now correct? Actually, I think it was stupid to differentiate this. Would have been much better to leave this. Let me see. Sorry, do you allow me to do this? Let me. So it was this, right? And here it was this. I think that's nicer. And then I have no 3, 1 plus w times mu, and I have this here, d3, and this is just 1 over a cubed, and this is nonsense here. Is that true now? Let me see, d mu by dt. No, there's still something wrong. So I want to have something with an exponent where the 1 plus v is in the exponent. How do I get this? Let me see. Yeah, wait a minute. No, it is true. It is true. So this, yes, of course it is true. 1 over mu is minus 1 plus w d by dt. So that's it. I think I can integrate this. So this gives ln mu, yes, of course. Ln mu is minus 1 plus w, and this gives ln a cubed. I have the freedom of choosing an integration constant. How do I do this? It's plus constant. And I can write this constant as ln of a constant, say CO. So then I have, if I exponentiate this, I have mu is a cubed, and this comes into the exponent, right? 1 plus w. If I exponentiate this, I get mu. If I exponentiate this, I get this, and the factor is in front of it. I think that's it. So I have, what I have proven is that mu of t times a of t to the power 3, 1 plus 1 is a constant. And that's the law. Okay? That's it. Yes. So you see, for w equals 0, it is what we had before. For other values of w, we get other powers here. Here you see that for other values of w, you don't have the law that that you just integrate the density over the volume, and this is a quantity which is conserved. You have something else, and this is the internal energy which comes from the pressure. Yeah? So you have an influence of the pressure onto the conservation law. Okay, I will discuss particular cases of this. As I said, the three most relevant cases are w equals 0, w equal minus 1, and w equal 1 over 3. And I will not attempt to solve the equations in full generality, but at least some special cases I will treat. Okay, any questions on this? If not, see you on Friday.